Dr. Pushpita Ranjan Bhattacharya. We welcome you, sir, to this august occasion. I now request Dr. Madhuprata Bhattacharya, Head, Department of Physics, to kindly introduce the speaker. Welcome you, ma'am.
Respected guest, Dr. Saikat Chakraborty Thakur, Executive Director, Kalyan Bharti Trust, Mr. Probir Roy, our Chief Executive Officer, Heritage Group of Institutions, Sri Pradeep Agrawalji, Principal, The Heritage College, Dr. Pushpita Ranjan Bhattacharya, respected heads of the institutions, my dear colleagues, and beloved students. Good evening to all. On behalf of the Heritage College, I feel privileged to welcome you all in the webinar organized by the Department of Physics. During its only 4 years of existence under the University of Kolkata, our department has produced outstanding results to stand tall amongst other prestigious colleges. It is my pleasure to introduce our eminent speaker, Dr. Saikat Chakraborty Thakur, to the audience. Dr. Chakraborty Thakur completed his BSc from St. Xavier's College, Kolkata in 2002. He did his master's from Indian Institute of Technology, Kanpur in 2004 with the Best Master's Research Project Award. Thereafter, he finished his PhD in plasma physics from West Virginia University, Morgantown, USA. During this period, he won the Most Outstanding Graduate Teaching Assistant Award for consecutive 3 years. From 2010 to 2014, he was the postdoctoral employee in the Center for Energy Research, University of California at San Diego. He is the associate project scientist at the same institute now. Dr. Chakraborty Thakur is a member of many professional societies. He has published 44 international research papers, mentored a number of doctoral, postdoctoral, and undergraduate students. He had refereed a number of international journals. Dr. Chakraborty Thakur is the review panelist for US Department of Energy, Fusion Energy Sciences, US National Science Foundation, Department of Energy, as well as for the Basic Plasma Science Facility at the University of California. We are truly honored to have Dr. Saikat Chakraborty Thakur with us. Thank you for your presence, sir. Welcome to the webinar.
I mean, this is an honor for me to be invited and giving a webinar. So I have given a lot of talks and presentations in colleges and universities, but this is the first for a webinar, and there is a first time for everything. And I would beg your pardon, or please excuse me if things go wrong. This is the first time I'm trying this out, and as much as research we try to do, I'm not a really technologically advanced person. I think the students understand technology more than me. But thank you, Madhubrata, for such a wonderful welcome. And I would probably go over to the presentation now, right? Before I begin, let me tell everyone that I am mostly targeting this talk towards very junior scientists, like very young students, and all the general common people who might not be like deep into plasma physics or thermonuclear fusion, right? That's the expectation. So I have tried to keep this talk in the form of a storytelling session. I would love everybody to think about what I'm saying. On each slide, I have like little pointers to just think about it. I have tried to avoid as much as technical details and equations as I could. And if you want to go into more technical details, we can always do it in the question and answer session, or after this thing is over, I'll have my email ID circulated, and you can ask me questions, and I'll try my best to answer everyone. So again, thank you to the Heritage College, the physics department, and let me take you through this little story. And I take that we are all very curious people. We are all students of science or any subject, and I have set up a series of questions that I'll try to answer. Okay, so the first basic thing, why do we do science and why do we even think about energy? Why is energy something that people should think about? Why does the Department of Energy pay scientists, or why does the people in the world all over, you know, why to everyone energy is something to think about? So let's look at things, and I go back all the way to the olden civilizations. Like, if you ask the question, what sustains a civilization? What does a civilization build up upon? And if you look at all the older civilizations, the oldest ones, the Indus Valley, Mesopotamia, Sumer, ancient Egypt, you name any one of them, you will figure out that they build up their cities, they build up the pyramids based on large scale manual labor, probably aided by some domesticated animals. And then you have to realize that it was not easy. It was an extremely harsh life for a large section of the society. And I would not like to go back to that kind of a society, thinking about everybody. And then going forward, uh, mostly the use of large scale animals, domesticated animals, and forced human labor has actually powered civilizations, mostly for mechanical energy to move things, right? And unfortunately, some of them still happen today. And it is only, this was a very revealing idea to me, because we study science, we go through our bachelor's, master's, PhD, and everything, but we don't really think about many other facets of society. But it is really true that all ancient civilizations, no matter how enlightened and creative and magnificent, they were built on slavery and grinding human labor, because human and animal muscles were the principal forms of energy, right, available for mechanical work. And until the discovery of less expensive forms of energy, humankind, men or women, could not be free. That made the present life that we are enjoying possible. And in that sense, moving forward to today, if you just look around you, energy is everywhere. It's a term that you just cannot spend your life without. From flights to trains to cars to industries, lighting all over the world, it's just everywhere. And then you ask, when do we not have energy? That's exactly what happened with the Amphan cyclone a few weeks back, right? Right after storms or grid failures. I put up this funny picture of the lantern, because when we were kids, the lantern was an inevitable part of our household. And only through the development of energy production and energy distribution is that my mom probably doesn't have the lantern anymore at her home. And so these are things to think about. And if you look at different countries, and if you look at the development of countries, like, I think more important than finances, there's something called the Human Development Index, which many important parameters are included in that. Life expectancy at birth, how many years of schooling can a person get, the gross national income, everything taken together, you can very clearly see that it's a very strange curve. The curve goes vertically almost up until a certain HDI, like Human Development Index, and then it flattens out. So once you have reached a certain amount in the Human Development Index, pretty good. And it's totally dependent on the power or the energy that the country can produce and distribute to their own citizens. And the next thing we think that energy that's produced in the world is very unevenly distributed. And it's kind of sad that the most populous countries in the world, like India and China, do not produce sufficient energy for the electrification of their whole countries. But we are very hopeful. The gross domestic product of all countries, irrespective of the country, have gone up since the last 100 years. And it's always a very positive upgoing trend. So we are very hopeful that rural electrification will come up as time goes by. At the same time, the world population has also grown. It's if you look at the curve of the world population, it has grown by leaps and bounds in the last 100 years. And in the era that we are now, every 12 to 13 years, we are doubling we are increasing 1 billion people in the world. And so why am I saying all this? Because see, taking all these 4 points together, like access to more energy gives us a better life. Energy usage and the energy demand goes up with GDP. The GDP goes up with time due to better uses of technology. And then also the world population goes up. And sadly, the countries with the largest populations are not yet at the peak of the energy curve. So take all those 4 things together, like it's like an experiment with 4 inputs. And what you get is you anticipate a humongous increase in the total energy demand in the next 100 years. Most of the students who are listening to this talk today, by the time you will be taking up the whole responsibility of a society, or you will be in your jobs, the energy demand is going to be way, way more than what we can produce right now on Earth. And that leads us to one of the biggest challenges in the 21st century. There are many challenges, like healthcare, production of medicines, like vaccines and stuff like that, production of food. But if you think all of these, healthcare, vaccine production of food, storage of food, all of them need energy. You cannot do any one of them without adequate production and distribution of energies. And how do we solve that problem right now? What do we do right now? So right now, well, this is from the 1850s. There are still populations in the world that use wood as part of their energy consumption. We have hydropower, but the coal, oil, and gasoline makes the bulk, 80% of our current energy production mechanisms. There's a very small amount, and so you see, we are right smack in the middle of this fossil fuel era. If you look back in history, if you look at anthropology, and if you look back thousands of years, we have gone through several eras, right? I mean, we talk about the Stone Age and the Bronze Age and the Iron Age. Any historian looking us 500 years in the future would be calling us that we were the fossil fuel era, the fossil fuel age, right? And unfortunately, it's going to go away in another 100 years or so. So there must be some alternatives. And on top of the fact that the oil and coal will be gone in about 100 years or so, there are other problems. Climate change is a huge issue. I mean, this is a funny, I got this cartoon, I loved it. Like penguins are rebuking human beings, saying that you humans have learned how to make energy, but then by using fossil fuels. And the health issues due to pollution are slowly catching up. And unfortunately, most of the Indian cities are now as bad as the Chinese cities, where they use large-scale coal, based energy production, because we all know all the pollutants that come out in the process. So there are more issues other than just availability of coal and oil. I always, when I work with my students, undergraduate, high school students, when I talk to them about the energy crisis that we are facing, I always say that we did not get out of the Stone Age because we ran out of stones. There are still stones in the world. So it's not necessary that we should go away from fossil fuels. Only if fossil fuels go, we end all fossil fuels in the world. Even if there are fossil fuels, deep in the mines, if we have a better technology, we should go over to better technology. I think that's the part of humanity we should believe in. And so the real challenge is not just energy. The real challenge is how do we meet the ever increasing energy demand and at the same time avoid harmful health and climate change issues. And in this plot, what you see is the blue is what oil and coal can sustain, for another few hundred years if we use all of the oil and coal in the world, which we should not because of other issues. But the demand is the red curve, and this huge shortfall must be taken care of. And to all of us listening to this talk, this should be something in your mind. This should be something in your mind. And so there are many possible answers. Of course, there are lots of scientists all around the world working on different things. Hydropower, solar photovoltaics, solar thermal, wind, biofuels, geothermal, nuclear energy, and fusion. All of them, all of these other than the one in the red box, are currently used technologies. All of them have their pros and cons, and none of them can win over the whole world. And in the energy sector, because I work in this institute, or the research institute called Center for Energy Research, so we have to mix with different people from the energy sectors, and we think that there is no one person taking the cake, all of it. We should work on and do experiments and do research and study and try to make all of these better. And a synergy of all of them taken together is a summation of all of these technologies that I have laid out someday is going to fulfill our energy demand without being too much of a burden on the pollution and the climate change of the world. And so today, just because it's, I mean, Dr. Madhubrata Bhattacharya and I decided that, let's talk about a futuristic vision. Let's talk about a vision of energy production that is not there in the market right now. A lot of people have been working on it. It's been a big challenge. I think it's a challenge as big as, flying. Like since the early days when human beings saw birds, we wanted to fly, but then it took us thousands of years to, control the air, right? And so fusion is something similar. And so let's go into the thermonuclear fusion. And so what is thermonuclear fusion? Like before even going into the definition, just colloquially, it's one of the really, really important holy grails of physics. And it gives us the future of humanity. Like if this technology works, we are in safe hands for a long, long, long time, for thousands of years. So we would not need any other sources of fuel for thousands of years. It does not lead to global warming or pollution of any kind. There is no risk of a nuclear accident, like in the, like Fukushima or Chernobyl, in the case of fission nuclear reactors. And there are very small levels of nuclear waste with a very short lifetime where we can easily tackle, and understand how to safely work with it, work with the very low levels of radioactivity. If you have not seen these pictures, this is like, the brute force that I was talking about, that why we should go away from brute force methods. And why is it, this is a picture about, we have energy everywhere, but we don't have energy if there are storms and grid failures. And that's the time you really understand the importance of energy production mechanisms, right? And this is the plot where I was showing that the human development index depends on how much energy we have. And again, energy is unfortunately not uniformly distributed across the whole world. And the fact that all the countries, highly populated countries like India and China, are growing in their economics. And as we grow up in the economic ladder, we demand more and more energy. And as the population of the world increases, taking all these four things together, we anticipate a huge increase in the energy demand, right? This again shows that 80% of our current energy demands come from fossil fuels, which is inherently bad because of climate change and pollution. And then we must somehow fix the shortfall to other means. There's already a lot of work on present day technologies which needs a lot of improvement, because only 12, all of these renewable technologies contribute to only 12% of the current energy demand. That's because they are usually way more costly than using coal and oil and gasoline. And as much as we love science, the business community would not accept a new business model unless it's cheap enough. And so there's a lot of work going on in the current day technology, energy technology, but today we are going to discuss about a futuristic technology where a lot of science has been done, but we are going to work on it. And so basically, this is where we are coming to fusion. Again, I apologize if this is too simple for everybody, but I wanted to avoid a lot of jargon, a lot of technological, like technical words. But we know hydrogen and heavy hydrogen have two isotopes, the deuterium and tritium. When deuterium and tritium can fuse, the nuclei of deuterium and tritium can fuse, they produce an alpha particle, like an helium particle, and a 14 MeV neutron. So the energy of the alpha particle and the neutron together is like 17.6 million electron volts. And that is a humongous amount of energy. It comes from the mass difference between the input and the output products. And again, the most famous equation in the world, E is equal to mc square, that tells us how much energy we can produce. Why are we trying to do deuterium, tritium, like DT reactions? Because if you look at the reactivity and the cross sections and the temperature, that's when we see the maxima happening at least possible temperatures. And so that's what we are going to try first. So, the reason why this is so difficult, there have been a lot of technological advancements in the last century. We send a man to, we send like two people to moon, right? And we have nuclear fission done. We have enormous advancement in space technologies and satellites, and yet we could not get fusion done. And that's primarily because starting fusion is very hard, mainly because you are talking of using nuclei which are already positive in charge. And we know this long range electrostatic repulsion, right? That's what Coulomb forces are. They would repel until and unless you can make the nuclei go really, really, really close to each other in the order of like 10 to the minus 15 meters, where it would be taken over by the nuclear force. And if the nuclear force, which is attractive in nature, wins over the repulsive electrostatic repulsion, only then we can have fusion, right? And so it's a balance between the two. So the next question is, what can we do? As scientists, as physicists, as people who are thoughtful, what can we do? What can we do in an experiment which increases the probability of getting fusion? First thing is if you increase the number of particles, so that means the density. Number of particles, number of nuclei per unit volume means the density of particles. So if you can get a very high density, matter, and now when the nuclei can come extremely close to each other, how can they come? If you give them a lot of energy to begin with, which is effectively the temperature of the system, right? So if you go to a very high density system, a very high temperature system, and if you allow the nuclei to be in contact with each other for a long enough time, where the nuclear force can act, because nothing is instantaneous, it takes time. And on an average, when you allow the system to be stable at a very high density and a very high temperature for a very long time, then you can actually, get fusion going on naturally, sustainably. It's called the Lawson criterion. It's like 5 times 10 to the 21 in the units of keV seconds per meter cube. And on the Earth, on the pressures and densities that are possible on the Earth, we expect these to happen around 150 to 300 million degrees centigrade. And I just wanted to note that this is 10 to 20 times hotter than the temperature at the hottest point in the center of the sun. So that is the challenge that we are working on. We have to make something 10 times hotter than the sun, and we have to store it in a bottle so that it's not uncontrolled. Now, I am throwing this word plasma while talking about thermonuclear fusion, because at these temperatures, you don't have anything in the solid, liquids, or gaseous phase. Everything is in this plasma state. Now, I don't know if everybody of you have heard the word plasma. I had definitely not heard about it until I went into my master's program and happened to do a summer project in Shah Institute of Nuclear Physics. It was just a pure accident, and it was a lucky accident. But so let me explain to you what it is. So, think of ice. If you heat ice, it will melt into the liquid. Ice is a solid form. It will melt into liquid, which is water. If you heat it up even more, it will go into the gaseous phase, right? So you have solid, liquids, and gases. And most of our school, we have been taught that there are 3 states of matter: solid, liquids, and gases. Now, a curious person can ask, what happens if we increase the temperature even more? What will happen to that ice turned into liquid, turned into water vapor? What happens is chemistry kicks in. That is the realm of energy in the world where you get chemical reactions. Electrons can go from one to the other, molecules, but you don't have dissociation of the nucleus. So this is still not nuclear physics, right? This is just chemistry going on. But even if you have, say, all atoms, all the molecules have dissociated into the component atoms. Even if you keep on increasing the energy of the system, what happens is you can actually knock off an electron from that atom. And now, instead of a neutral particle, you end up with millions of negatively charged particles, which are electrons, and the remaining positively charged ions. And if you are pumping in that energy, this state becomes a stable state. So this is a state where you have some neutral particles, some electron, and some ions. And this phase, when you have enough number of ions, whether it is partially ionized or fully ionized plasmas, so this state is called plasmas. This system starts showing collective behavior. As opposed to work that is done in CERN, you might have heard about particle accelerators, right? You take each particle and you accelerate them. I just told you that ionized gases, hot ionized gases, can be thought of as plasmas. it's called the fourth state of matter. And if you look for examples around you, naturally you don't find them. They're very rare. Lightning is an example of plasmas, naturally occurring plasmas, and the aurora. And then again, it's for the students to think about, why don't you find plasmas on the earth? Because the earth is too cold. The earth is too cold for plasmas to occur naturally. It's like inside your freezer, like in the deep freeze you call, you don't find running water because it's too cold. In that conditions, the state of water which is stable is actually ice and not running water. And so similarly, plasmas are very, you see plasmas in very hot places. But then if you think of beyond the earth, say our sun, all the stars, the galaxies, the intergalactic medium, the supernova explosions, they are teeming with plasmas. So, and because plasmas are so hot, they emit light, they can emit photons. And so what you see, like when you do astrophysics, you are studying plasmas. The first thing in astrophysics that's taught is probably, the Shaha equation and, the dispersion relations of cold plasmas. And so 99% of the visible universe is made out of plasma, and yet on Earth, we don't see much. But then plasmas have a huge amount of industrial presence. So, all the lighting that you see, the neon glow discharge lights, the plasma TVs that have now been discovered, spacecraft propulsion, once you have crossed the gravitational field of the Earth, because gravity is very strong, you need chemical rockets. But once you are up in space, very small nudging can sustain you for a long time, and you don't need so much of the weight of the chemicals. So spacecraft propulsion, thruster technology, and recently this plasma medicine is making a big, effect in medicine, in health sector basically. And so we find examples of plasmas everywhere in a lot of places. And in fusion is that you have to go to this humongous temperature, like millions of degrees of centigrade. And at those temperatures, inside that fusion reactor, it will be plasmas only. No other, nothing else. Whatever goes in, it will become in the plasma state. And then understanding the properties of plasmas, from a physics point of view, from a pure physics point of view, is extremely important. And so, like plasmas is like a hot gas, but in addition to just having all the properties of the kinetic theory of gases, it contains charged particles, electrons and ions. So there are different species. The way they collide with each other is different. Electrons are extremely light than the ions. The ions are massive, and so you can imagine that neutral collision is going to be very different from electron-ion collisions or ion-ion collisions or electron-neutral collisions. So it's a very challenging topic to work with. It can conduct electricity, just like as in a wire, and because you have mobile electrons and ions, it can conduct electricity very well, very low resistive, physics. It can respond to magnetic fields, and it can exhibit collective behavior that I have said before. By the easiest example of collective behavior is like a drop of honey, or something with a very high viscosity. So and so you have the equations of hydrodynamics coming in the way, but also electromagnetism, Maxwell's equations and hydrodynamics taken together would give you something called magnetohydrodynamics. And all of these are important in understanding what plasmas are and how plasmas behave. And unless we understand how plasmas behave, we cannot do fusion. Right? So that's why I have this slide from a pure physics point of view. Now, the good thing about this is that since external magnetic fields can affect plasmas, we can use them to control plasmas. This is a very simple thing, that if you have a charged particle over a magnetic field, you have this thing called a gyroradii, right? And if you have a small parallel velocity, the particle will helically wind and move across the guiding magnetic field line. So these are called guided drifts. And this is an example that if you can take the magnetic field and wrap it around onto itself, then you can effectively confine a particle, right? So I am trying to show an animation. Please let me know if this works. So this is a very simple example, extremely simple example, that if you have a toroidally shaped magnetic field line, and if you have a charged particle, it will just wrap onto itself. And so in this particular example, this will be a wonderful method of preventing very hot ions from going and touching the ends of the torus. See, the torus is like a, what do I say, like a bicycle tire, right? and this is the tube inside the bicycle tire, and you don't want the tube to touch the edge of the tire because otherwise it will melt. You don't want the system to melt, right? So this is one way of confining plasmas using magnetic fields, and this is called magnetic confinement. Now, this was a very simple example just with one particle. When you have like 10 to the 20 particles per meter cube, that's the densities which we work on, it's hard to keep track of everything, and then you actually get collective phenomena. You have to use kinetic theory or magnetohydrodynamics to explain those, and it becomes a very dynamic system, and they are extremely unstable. It's as unstable as cyclonic weather. So a uniform magnetic field, like in a solenoid, can easily trap charged particles, but they would get lost at the ends, right? So that's why we take a solenoid, you turn it around, you bring it into a shape of a toroid, and we hope that you would get confinement. Unfortunately, as soon as you change the shape from a cylinder to a torus, you no longer have, you have these things called a curvature. A curvature drift comes in. You have spatial inhomogeneity because the way you wrap the magnets, if you can just imagine that the inner side of the magnets are closer to each other than the outer side just by the geometrical construction. And this causes a spatial inhomogeneity. It brings in gradients in the magnetic field. And these cause the plasma to ooze out, if I can use the word ooze out very colloquially, from the center of the machine to the edge, and it can harm the machine. So a pure toroidal field, will not work. Now, people have tried saying that what if we drive a very strong current through the plasma? Will that stabilize the system? Now, unfortunately, it did not. So then in the 1940s and 50s, this was the technology initially people tried and thought that a large current can probably stabilize the plasmas. Unfortunately, there are lots of instabilities, and we have this thing called the sausage instability because it looks like a sausage, and then this thing called a kink instability. Kink instability is a very common phenomenon in nature. If you take a spring, any spring, and press on it from two sides, you will find a kink instability. And this is just some images that has been done in Princeton, and the plasma was stable only for 20 microseconds. So you can only imagine the challenge that scientists in those eras had, because they did not understand the details of plasma physics while trying to work on fusion. So based on all of their experiences over the years, we are now in a much better place. We are luckier, we understand things better. And in Russia in the 1960s and 70s, they came up with this concept called a tokamak, which is an acronym for a toroidal chamber with an axial magnetic field. But on top of the axial magnetic field, which gives you the toroidal field, you also have something, if you can follow my cursor, if you can follow my pointer, so these external magnets produce a magnetic field in the axial direction, right? I mean, in the toroidal direction. But when you have the plasma and a high density, highly charged, high current plasma, all of you know that current also produces a magnetic field, right? So a current moving in the toroidal direction can actually produce a magnetic field given in these green circles in the poloidal direction, right? If you just follow basic simple rules of electromagnetism. And then the net effect is that a externally applied toroidal magnetic field can add, linear. So the externally imposed toroidal magnetic field, which goes around the main body of the torus, right, around the torus, and the combination of a magnetic field that can be produced by the plasma itself, because plasma can carry current, right? Plasmas are charged particles. So that produces a poloidal field, which is the short way around the torus, the green curve. The combination of these two actually produces a helical magnetic field, right? The magnetic field is now a superposition of these two, and that provides the stability that people have been looking for a long time. This was, along with this, people found that if you play around with how much energy is put into the plasma itself, what are the conditions of the plasma, how clean can the vessel be so as to reduce the impurities, if you shape the plasmas well, a combination of different experimental techniques in 1981-82 led to the discovery of something called a high confinement mode. And in the H mode, because it's just high confinement mode, H mode, we can successfully do fusion, and we have showed examples of successful fusion being done. However, there are plasmas are a very how do I say that? It's like a very naughty child. You expect it to do something, but it will again do something else. If you may allow me to give that example, they're very delicately balanced with regimes of tremendous extremes. So let me give a few examples. You want the center of the plasma to be 10 times hotter than that of the sun. Otherwise, we don't get fusion. But you don't want that plasma, that extremely hot plasma, to touch the walls of the machine, because otherwise the walls of the machine will get destroyed. We still use like tungsten or as the walls of the machine, because that's one of the strongest materials we have. But it melts around like 2000 to 2500 degrees centigrade, depending on the grade of the tungsten. So you want the edge to be cold. Now, when you have very hot something beside very close to something which is cold, this will lead to very strong gradients, right? I mean, basically the temperature and the density of the plasma is going to change very rapidly within a very short distance. And whenever something changes very rapidly within a very short distance, you are going to produce very strong instabilities. And the instabilities can go crazy. Just like, an example is, you will hear this in the weather reports, that high pressure zone and low pressure zone. So we have a high pressure or a low pressure system. They produce like the wind, and the wind, when their winds are very strong, they effectively become thunderstorms, right? And can become very destructive, like cyclones. We had one back in Kolkata a few days ago, or like a few weeks ago. And so we have to deal with these instabilities if we have to get fusion going. It's inevitable just by the way it is constructed. You cannot have a hot plasma touching the walls of the machine. You cannot have cold plasma at the center of the machine. Otherwise, there's no fusion. So, this is a challenge that we have to face as people in this field. Let me go with another example. Another challenge is that even with the highest magnetic fields possible that we can make on Earth, the plasmas are very unstable, and it will inevitably leak at certain locations. You can imagine this as if you have a balloon which has a pressure, plasmas of pressure. So this is a cross section of one of those tokamaks, and you can imagine this is a balloon, and you are trying to reduce an expanding. You don't want the balloon to expand and hit the wall, right? You are trying to reduce the expansion of a balloon using rubber bands, and as best as you try, you cannot have infinite number of rubber bands. And so in between where the pressure of the bands are, there will be leakages of pressure of the balloon. And exactly some similar things happen in tokamaks also. Again, you can also think of the edge of the tokamak. The edge of the tokamak has like humongous amounts of instabilities. I mean, sorry for using these colloquial terms, but what I mean is high intensity instabilities. Think of boiling water. If you watch boiling water from the side, you can do that at home anytime. You will find little bubbles bursting, and when the bubbles burst, they spray the hot water to a particular height on top of the surface of the boiling water. And similar things happen at the edges of any two different material, like at the edge of the sun, where the solar the solar plasma ends. You have solar flares, which sometimes are directed to the Earth. And similarly, these plasmas ejected from the edge of the tokamak plasmas will eventually hit the walls and degrade the walls. And then, so our whole effort is to how to reduce the blobs. We call them blobs, the little blobs of plasmas coming out. And hence, there is a lot of effort to understand how these blobs, even though they are lower temperature than the core is hotter, but even at the edge, the plasmas are very hot, with respect to temperatures that we understand in the world. How are they going to degrade the material? Because that's called the field of plasma material interactions. That will eventually determine the lifetime of these fusion devices once we have them commercial. This is just an example of what challenges we face. So let us just quickly go over through what is the current status. So tokamaks have been around since the 1960s, of different sizes and shapes, of different densities and different magnetic fields. And with each experiment, we learn a little bit. So you can see on the left-hand side that this color represents deuterium-tritium operation, because tritium, once you put deuterium and tritium, the neutrons coming out from the reaction. Remember, the reaction was deuterium and tritium giving you alpha, like alpha particles and neutrons. Now neutrons are neutrals. They are coming off at 14 mega electron volts, so you cannot stop them because they're neutrals. They don't get affected by the magnetic field. So they can embed into the tungsten or the wall material and make it mildly radioactive. So once you have a DT reaction, we are not allowed by the respective governments of the respective countries to do any other kind of experiments. And that's why you see only very few, like there's 2 examples all over the world that have actually tried those reactions. And there's a wide variety of different kinds of experiments that have been done. And based on the knowledge of, really we are on the shoulders of giants in this case. So over the last 40 years or so, well, now like 60 years, we have gained a lot of experience. And I want to show you where we are right now. See, back in the, you remember, I showed a few slides earlier, this criterion called the Lawson criterion, right? That was the density times the temperature times the, how long can you hold the density and temperature. So N, T, and tau, where tau is the time scale, right? And so that is what is on the y-axis, and it is in a logarithmic scale, right? So every line here is 10 times better than the one below it. And as a function of time, since the 1970s to the, like 20, we are around 2020 now, right? See, in this, we have improved the yield, the fusion yield, by several orders of magnitude. Like it's not like 5 times, 10 times. It's actually hundreds, millions of times. We have improved it millions of times, this performance. And something we understand more common to us because all of us use it is the Moore's law in semiconductors, saying that the number of, the memory in a chip can be doubled every 2 years, right? That's what the Moore's law is in a transistor. And that has allowed us to, go from big, huge, super like computers with low memory back in the 1970s and 80s to a smartphone, which is as good as a laptop, right? And if you plot them side by side, I mean, fusion yield has actually grown. The yield has grown at a much faster pace than that. So it's like every 1.8 hours. So a lot of people think fusion is hard and fusion can never be done. But we are hopeful. We have to live with the hope that in spite of the fact that it is very difficult, we will give our best. And with a lot of theory and experiments being done side by side simultaneously, we'll try and see where we are. Now, what I want to talk about next is this thing called ITER, like ITER. It's the International Tokamak Experimental Reactor. Anything of this scale, this is actually the first time in the world people are coming together at this scale. More than 50, well, there are, the whole of the European Union, which has like 27 countries, well, and England now, which is separate now, and USA, Japan, Russia, China, Korea, and the last country to join was India, like I think around 2014, 15, or maybe a little earlier. So all of these countries have come together unanimously, independent of their political beliefs, independent of their cultural beliefs, independent of whether they are fighting at the borders or not, to make sure that fusion is something everybody concentrates on. This is something no individual country can do on their own. And I did not have it here written down, but in 1985, when the first meeting was done between the, it was the Cold War era, for those who of you are aware of it, between, the Russian and the American presidents, the only thing they agreed upon, the only thing in that meeting they agreed upon was declassification of fusion. Until then, fusion was done by the military of the respective governments. That was the only time they agreed that this is too difficult on its own, and let us come together. And so this is, that was the brainchild in 1985, and the 2025 is supposed to be the first plasma in this machine. It's supposed to produce 500 megawatts of fusion power, where only 50 megawatts is the input. So this is going to be a self-sustaining fusion reactor with 10 times the yield. So that's, we call it Q. Q is the yield, greater than 10. It is being built right now in Cadarache in France. And this is just because I have a lot of friends here who work on this tokamak called D3D. is the largest one in US. But still, this is D3D and it's the largest tokamak in US. And this is one of my friends inside the tokamak. This is the inside. When he's working on it, he's fixing things, and these are different antennas to heat the plasma. And this is a picture of when the plasmas are actually on. Most of the radiation is actually not in the visible spectrum, but you see this glow in the thermal, this is a thermal radiation coming out. But you have lots of X-rays and ultraviolet coming out also. But with respect to D3D, ITER is a huge engineering challenge. Just to show that this is what you see. This cross section is this cross section, but then you can imagine how it has been expanded to the ITER regulations. And this is the holy grail that we are all depending on now. This is a picture of the site where it is being built. And I'm proud to say that India has a big part in building this. They are building the main vessel inside which the whole tokamak will stay. You see, this is being built there now. And it's an industrial scale experiment. And yet, for all the students who want to be mechanical engineers later on, or electrical engineers, or civil engineers, there are more than 1 million components at this scale, and yet the resolution of precision has to be in the order of millimeters, because we are going to produce these magnets in a segmented way, bring them all together, assemble them. These magnets are superconducting magnets, so you will have to have like the coolant flow through them without any leakage. Yet when you increase the magnetic field, and when there is so much of current involved in the system, so much of heat involved in the system, when you have this amount of heat, things expand. And right, so there are going to be extreme amount of stresses and strains. And so scientists all over the world have spent like years and years trying to theoretically understand the system, predict the system, and then come up to the engineers and come up with engineering designs. And only then experimentalists are now getting involved. And it's such a humongous project that this is in Cadarache in France. The site had to be chosen carefully, not in an earthquake-prone zone, not in a flood-prone zone. We didn't want another Fukushima or something like that. And so the nearest but individual components are being built in China, in India, in Japan, and being shipped over there. And it's not a port city, right? It has to be away from the flood-prone areas and earthquake-prone areas. And so the French government literally had to build new roads just to accommodate the fact that you are bringing in heavy industrial equipment from other countries. The port used in Marseille. So this is just another angle. This is a more recent, and this industrial setup is coming up. We are excited about that. And this is just a model just to show the size scale. So this is a scaled down model, but it's to scale. And you can see, like we joke, this is a 6 feet tall French person. And you can see the concept and how the structure and the size and the scale of the system. And it was necessary because of all the theoretical work done over the last 10, 20, 30 years, which can predict that you need this system to get a fusion output 10 times larger than the input power that you are putting in to keep the plasma going at the very beginning. Because you have to start the plasma. To produce the plasma, you need energy. You have to turn it on. Once the fusion starts kicking in, the fusion itself is going to produce energy by E is mc squared. And that will sustain the reaction. And we can still get 10 times more output, like 500 megawatts with 50 watts of input power. And there are still a lot of research topics that people are actively working on. We call this a burning plasma. We are still worried about confinement. People are working on different kinds of confinement. There's a lot of technical names. I don't want to go into the names. I can come back if you have questions about it or later on. But the stability issues, can you control the plasma? Can you control the position or the location of the plasma inside the chamber? What about the power, the energy that comes out? How are we going to tap that energy? Because there is this thing called a blanket. So the blanket will absorb the heat, and the heat will then, through pipes, go into like boiling water. The boiling water will turn into steam and turn a turbine. That's how we are going to generate energy out of this system. And you need a lot of diagnostics. Like when I say you want to go to 150 million degrees centigrade, how do you know that? So you have to have diagnostics, right? You have to measure them. And so fusion is, it's not just a single thing. It's just a name, fusion, but it's actually engineering, experimental physics, theoretical physics, material science, all coming together, for a grander goal. And this is just a fun thing I show to my students. It's like it's all about heat. You have to put the heat in, you have to keep the heat in, and then you have to keep the heat out. But what I mean by heat in each different circumstances is different. You have to turn the plasma on, you have to make sure that the plasma is stable and sustained. And then you have to make sure that the energy that is coming out is properly captured and can be utilized to produce electricity as we understand, right? And 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 let me conclude by some just perspectives. Again, this talk, I thought it's more on the form of a storytelling that we believe ITER is so challenging. It's a challenging engineering task that when we started, we were not sure of how difficult it would be. And so now we compare it to some of those things that have, we can probably send a man to the moon again. But the first time is always the most difficult. The first time you do something. The first time, like, building the International Space Station, the first time people were sent on the moon. We compare it to them, but technologically we think it's harder because, a single country could not actually do, sustainable fusion reactions. We couldn't do that yet. Now, again, as I said, it's an industrial scale structure with like millimeter resolution precision. So, again, anybody who has built anything, like if you have built a chair, if you have built a probe in a lab, if you have built an experimental setup, you will realize how challenging that task is. And again, so see, you have the hottest, once this is working, this would be 10 to 20 times that of the sun in temperature. So you have the hottest thing in the solar system, right? It's hotter than the sun. And yet, right outside the vessel, you have those magnets, which are superconducting magnets, and it has to be cooled by liquid helium, which is like 4 degrees Kelvin, and within like close proximity of each other. And you have to avoid all kinds of accidents. This machine is in such scale that only one accident is allowed. The whole thing will shut down. So basically, no accidents are allowed, right? I'm just joking. So, this would again be the first demonstration of achieving Q is greater than 10 with all the technical know-how necessary. So this is still not a real power plant. We're going to take the power out, but this is not connected to the grid, the electrical grid which sends electricity to our homes. So that is going to be on the next experimental reactor called demo. And this is basically an advertisement to the Bill Gates of the world, Jeff Bezos of the world, and the rich people of the world who want to conquer the energy sector. And we have not successfully done fusion yet, but we can imagine that we are getting closer and closer because there are at least 10 different industrialists pumping in commercial money into the study of fusion, which is very rare when they don't have an idea if it will give them a feedback or not. Until now, all research funding, just like NASA or agencies like NASA, was done by the government only. So that is something people say beyond physics. That's something like the people have hope. Until now, only scientists had hope. Now more people in the society have involved. And again, this is an example of so many countries coming together. This has not been done before. And I just hoped that during this COVID-19 issues that we are still going through, that many number of countries actually agreed with each other and came together, which is unfortunate. So this might, in future, this might be another example of how countries can come together in spite of all their differences in culture and politics and so on and so forth. So again, people, we are skeptical. As scientists, you have to be skeptical. You hope for the worst. I mean, you hope for the best, but you design thinking that what could go wrong, and then you make better. You want to be better than that, right? And so we really think that, why is it taking so long to do fusion? But we have to understand a lot of things are at stake. A lot of things are at stake. It's very similar to, we have been thinking, since the first time human beings saw birds, we wanted to fly, but it took hundreds of years before we can actually start flying. But between starting to fly and conquering the air, it just took a few decades. Between a few decades, you went from not being able to fly to like aeroplanes all over the world, right? And so that is what a lot of people are hopeful, in spite of all the successive previous experimental failures that we have learned from. We have learned from every time something went wrong. We have learned from it, and again, there are a lot of positive side effects. So even if fusion is not done yet, there's a lot of positive side effects, and I love this one because most of us don't know it. So back in the 1970s, people were trying to figure out how can we increase the temperature of the electrons? How can we increase the temperature of the ions inside the plasma? Because we have to heat them up to 150 million degrees centigrade, right? And while doing that, they actually, like inadvertently, they just by accidentally discovered that there is this thing called radio frequency technology. Using RF waves, you can produce very high density but very uniform, without any instabilities, like plasmas. And that led to this revolution called the semiconductor revolution, where it's actually plasma etching. So you take a semiconductor, right? You take silicon. You have to make little grooves in silicon, and then you have to dope them like NPN junction, right? You know it about, that's how you make transistors. That's how you can get computer chips. Previously, back in the 1970s and 80s, this was done by photolithography and chemical etching. So you have to, it's chemical etching is similar to kind of taking a biscuit and putting it in hot tea and then pulling it out to see how much of the biscuit has been affected. The problem, you all know what the problem is. You do it too less and it is still very hard. You do it too much and it melts away, it goes away from your hand, and it's horrible, right? And so chemical etching was a very inefficient process. And you had, the grooves between transistors could be brought closer to each other only in the order of micron sizes. And the computers, that's why in those days were very large, like a fridge or an Almira, whatever. And only in the 1990s and throughout the 2020 like 2000s, basically, because of plasma etching, you can make very thin, nice grooves, because see, plasma have ions, and if you accelerate the ions, it will come and hit your semiconductor, like the silicon, and that is more like hitting the surface with a very thin, narrow, like spade, like each individual ions. And you can now make the grooves in the order of a nanometer, like 20 nanometers. And thus you see how the plasma technology has actually effectively made your smartphones, because that's what it is. The whole laptop, instead of being the size of like a fridge, it's now the size of you hold it in your palm, and some of you are watching this with this. So it's a challenging thing when you are trying it out with lots of scientists taken together. You end up getting a lot of good side effects also. That's my take. And so I will end here and probably open up for questions.
We have a lot of questions from inquisitive minds. We will now go for a very brief question answer section. The first question will be asked by Raj Aryan Ray. Raj.
Good evening, sir. This is Raj Aryan from the Heritage College, Physics Department, first year. My question to you is that, as you said, plasma, due to free charges, is affected by electric and magnetic fields. Electric fields gives it an acceleration, and magnetic field causes it to rotate in a circular motion. This plasmic matter, when gets collided with some obstacle or is interrupted by some electric or magnetic field, results in the dispersion of light, which we commonly see as aurora borealis on Earth. So
Yes.
I want to ask.
Okay, go ahead. Yes.
Yeah, so I want to ask that how and why the light gets dispersed by the intrusion of electric and magnetic field in some highly condensed plasma like sun flare. Thank you.
Right. Thank you. Very, very interesting question. Let me say, so just a few things. When we use words in science, like in physics, it has very technical specifications and meaning, right? So I think the word you mean is not dispersion related. Really, dispersion is a very technical thing, right? How the wavelength changes. But what actually happens is, remember I talked about little bursts of plasma coming out from the edges of plasma. Now the sun is a ball of plasma, So at the edges of the sun, you have little burps coming out. Those are those solar flares. It follows the magnetic field, and it comes towards the Earth. Now the Earth has a magnetic field. Now can you can watch me, right?
Yes, sir, I can.
Okay, so imagine my hand is the Earth, right? It's a sphere. Okay, but the magnetic field of the Earth is like a dipole. So you have dipolar magnetic field. Now the plasma from the sun is coming and hitting the magnetic field, but it cannot penetrate the magnetic field. Just because you said when there's magnetic field reconnection, the plasma have to follow the magnetic field lines and go to the north and the south poles. As it goes to the north and the south poles, it has a lot of energy. It's coming out from the sun, right? It's a very energetic, high temperature plasma. As it goes to the north and south poles, it actually collides with the nitrogen or the oxygen or the carbon dioxide in the upper atmosphere, and it is just simply emitting the light. It's not dispersion. It's just simple light emission because the nitrogen is gaining energy due to collision of an ion that comes out effectively from the sun, and it's an electron transfer in the nitrogen levels. And that's why you can actually do spectroscopy of, say, the aurora and figure out, what is the composition of the upper atmosphere, because the light came from there. You know what I mean?
Thank you, sir.
I don't know if I answered your question, though.
Yes, sir, you did, sir. I'm really thankful.
The second question is from Disha Roy. Disha?
Yes, ma'am. Good evening, sir. This is Disha Roy from first year physics department of the Heritage College. So my question to you is, how can the magnetohydrodynamics help in the solar wind acceleration?
Right. So magnetohydrodynamics is actually the study of how we understand plasma. It's like hydrodynamics for waves, just for neutral, for water, for waves, for like a tsunami. When you can understand those systems using using the method called hydrodynamics. Similarly, to understand plasmas, we use magnetohydrodynamics. It's like you start with the equations of hydrodynamics, like literally Navier-Stokes equations, or like the standard conservation equations, like momentum conservation, charge conservation, mass conservation, and then you add on to that, because plasmas have electricity and magnetism involved, like the Maxwell's equations. You actually end up getting a set of equations which describe the system. So it's not necessary that magnetohydrodynamics is helping phenomena. It's actually trying to understand the phenomena. So, for example, hydrodynamics does not help a tsunami, or hydrodynamics does not help, like in the actually it does. Using hydrodynamics, you can predict what will happen if you do something. In that sense, magnetohydrodynamics helps us in understanding, like plasma stabilities and instabilities, global modes, and I mean, the amount of material that comes out from the sun in a solar flare is so large. Like a solar flare can be hundreds of times larger in size than the size of the Earth. So maybe technologically we have never used like magnetohydrodynamics to control anything of that scale. But yes, we can predict a lot of things. And at smaller scales, MHD helps us in understanding and predicting how to control different plasma phenomena. Maybe not solar flares, but other things.
My name is Parthotim Sanyal. My question is, why don't we use muon catalysis in large scale?
That is actually, I'll be honest to you, I don't know the answer to that. I'll find it out and tell you, because, that's, I don't say anything wrong when things are not in my line of expertise. Yeah, I don't know. I'm sorry. I will not give you any wrong, hand-waving arguments, but I'll find out and let you know.
The final question from Satyajit Chakraborty. Satyajit Chakraborty.
Good evening, sir. This is Satyajit Chakraborty, a first year student of the physics department, the Heritage College. Sir, as you told that plasma is essentially ionized gas, so we can consider it to be a fluid. So how exactly is the fluid model applicable to plasmas? How exactly can we apply all the laws of fluid mechanics to plasmas?
Most. See, in fluid mechanics, what you don't have is, so okay, imagine you have a glass of water and you are describing it through hydrodynamics, right? You have various toxic equations, and it's like a pressure balance and everything.
Yes.
But it's a uniform thing. It's only one thing,
Okay.
right? All the molecules are behaving uniformly. So you
Okay.
have waves and pressure, propagation of waves and stuff. But
Yes.
plasmas, it becomes more complicated because now you have, like ions and electrons, and you never have 100% ionization is very, very hard. So you,
Okay.
typically, there are always a lot of unionized, like neutrals.
Okay.
And also you might have impurities of a different gas altogether. So when we are trying to do, say, hydrogen plasma, you might have a few particles of argon floating around, or the walls, like stainless steel impurities. So you have
Hmm.
impurity particles, you have electrons, you have ions, and you have neutrals.
Yes.
Now, all of them are not equivalent because they have different charges. Some of them have electrical properties, neutrals don't.
Yes.
And another very important thing to realize, which I myself did not realize this for many years, is that when something has a very different mass, like the electron is
Yes.
approximately say 1800 times smaller than hydrogen mass, right?
Yes.
So when we use argon, which has an atomic mass unit of I think like say 40,
Hmm.
right? So it's almost like 80,000 times heavier than an electron.
Okay. Yeah.
Very different. It's like an elephant and a rabbit.
Hmm.
I don't know. I have never measured an elephant and the rabbit's weight, but imagine it could be 80,000 or whatever. So they will have different properties. Their
Yeah.
mass, but the mass affects their speed. So the
Yeah.
when you look at a gyro radii, like you have a magnetic field and the particle is moving around the magnetic field. What
Hmm.
is the frequency of gyration? It's proportional to root over of the mass, and so and what is the kinetic energy? When we think of temperature, we just think of temperature as a single number. Actually, you will learn in your physics courses that temperature is actually a velocity distribution. Particles move at all random velocities. The net
Yes.
effect that comes to us as a temperature.
Yeah.
So the kinetic energy of like electrons and ions can be totally different. And so you can somehow think that this is a lot of, if you have 4 or 5 different kinds of liquids mixed together, I don't know, water and oil and milk. In that case, maybe, but then, water, oil, and milk do not have magnetic properties. And then
Yeah.
again, electrons are different because they have different charges. So I had no idea what I'm going to face, but I probably ended up in doing something which is so complicated that I don't understand fully yet. And
Okay.
but another thing, if this is the last question before actually breaking off, I want to just say one thing. To all the students, first year, second year, third year, I was just a very, very simple graduate, like student like you guys. I was playing soccer all the time. I was staying in a hostel. I don't eating dal, which looked like water, with a little bit of yellow in it. And so, I would say like don't lose hope. Don't listen to friends who say pure science has no future. I was lucky with amazing teachers throughout my life, and your teachers will agree with that. Actually, we went to the same college, and so just keep hope and keep struggling. Just keep chipping on it. You don't be a genius to do good things. You just have to be patient.
Thank you, sir, for the wonderful talk. Uh, if you have more questions, you may please contact the speaker through email. Now, I request my colleague Roshni to give the vote of thanks.
A great privilege to propose the vote of thanks to all the dignitaries there. On behalf of the Heritage College, I would like to thank our speaker, Dr. Saikat Chakraborty Thakur, for such an enlightening session. I would like to thank the staff of Kalyan Bharti Trust for giving us the opportunity to organize the webinar. I would extend my sincere thanks to Mr. Debashish Karmakar, System Administrator, for all the technical support necessary for the webinar. I would express my gratitude to Mrs. Suhasini Chaudhary and our Joint Registrar, Dr. Kavita Shastri, for her constant guidance and support. My sincere thanks also goes to Dr. Madhuprata Bhattacharya, Head Department of Physics, all the faculties and staff of this college for being there. but not the least, I would like to thank my beloved students for their enthusiasm and cooperation. Thanks once again for participating in such a wonderful and interesting webinar.